talking about local solutions regarding the Navier-Stokes equations and so on and so forth. It's the third time we see this picture today. I could use it Van Gogh's Starry Night or Hokusai, The Great Waves. But of course, Da Vinci is a classical example of turbulent flows. He was very ingenious, of course, but I believe he could saw the large and the small structures. And actually, Da Vinci was very not worth guy, because I mean, he was really able to observe the flight of birds in very good detail and at naked eye. So that was a difficult thing to do. So anyway, those are the complications of turbulent flows. Pinaki and Gustavo, they spoke about the different length scales and the continuous energy spectrum. And I took this picture from the internet. I missed the reference. But the idea is basically, that was mentioned before, you have this continuous spectrum of energy, which of course implies a continuous reference length scales and continuous time scales as well. So that's, if you really want to describe turbulent flow, you have this whole range of lengths and times that you have to resolve. And that's really the complication of turbulent flows. I mean, if you want to do direct numerical simulation of turbulent flows, you have to go to very, very tiny length and time scales. And of course, that's too expensive. That's too difficult to do. That's one reason. Second reason is, if you really want to do computations of turbulent flows, you've got to specify the initial and the boundary conditions. And again, that's a very difficult affair, because sometimes, in particular, in surface flows, the details of the surface are of the order of the length scale you have to resolve, and so on and so forth. But today, I want to speak about one particular problem. Those are examples of classical turbulent flows. This is homogeneous turbulence, the flow behind the grid. That's boundary layer flow. That's the free jet flow. And that's the weight behind a blunt body, a boat. Today, I want to concentrate or spend a few minutes, next few minutes, talking about turbulent boundary layers. So what I'm going to do, I'll do a brief historical reconstitution. I'll go through some classical stuff. And then I'll try to explain the two-layered model for the turbulent boundary layer. And then I'm going to explain how the log profile that Gustavo introduced a few minutes ago is invariant under different conditions. So again, so that's basically the problem we want to solve. That's a single picture of the turbulent boundary layer, and really we want to be able to describe all that complicated stuff. So what do? We look at mean properties, basically. The Navier-Stokes equation is supposed to embody all the features of turbulence. All the physics is there. The Navier-Stokes equation is known since 1823. So how on earth are we at this time struggling with the Navier-Stokes equation? And the key, again, is that we have to solve all that complex flow to very tiny length and time scale. That's a representation of the previous picture by Leslie Courvoisier. That's a classical paper of 1967, as Gustavo was mentioning. It is possible to see the viscous sublayer, the log layer, the wall region, the outer region, and what Courvoisier called it an interface superlayer. This is a graph in linear coordinates, and it took people 47 years, more or less, to get to this figure. And I'll go through history a bit here. That was the graph that Gustavo showed us a few minutes ago. I'll do some interpretation of the graph. There is this close to the wall viscous linear region, the logarithmic region, which is dominated by inertia effects, and the awake region, which is again dominated by inertia effects. So basically, there is one well-defined wall region, which is that illustrated by the red brackets, and an outer region, which is illustrated by the blue brackets. And I'll try to use perturbation methods to explain the two-layer structure of the turbulent boundary layer, depicted here by the red bracket and the blue brackets. So that's, again, a very simple representation of the previous slide. we have the dominant equations and the local solution for the viscous sublayer, for the full turbulent region, and for the outer diffract region. And in the very next few minutes, I'll be explaining that structure from the point of view of perturbation methods. Now, a bit of history. Some people mention that the logarithmic layer was first observed by G.I. Taylor in 1916 in one of his trips close to the Canada region. I went through his paper, and actually, he did measure that velocity profile. Those are actually measured velocity profiles. Those are his calculations, and he expressed the local velocity profile, the mean velocity profile, not using the logarithmic function. And that's basically the way he expressed the wall drag for his particular experiments. This is a classical paper as well, very often mentioned, Ludwig Prandtl, 1925. That's the paper that actually introduced the mixing length theory. It's all there. But again, where you really see the log law stated in a very clear way is in a paper by von Karman in 1930. And then he introduced it as reference length scales for the wall layers, U tau, the friction velocity. But the classical paper for the derivation of the law of the wall is a paper by Clark Blanchard Millikan, the son of Robert Millikan, and that was derived in 1938 in the International Conference of Theoretical Mechanics, which today is called the International Conference in Theoretical and Applied Mechanics. The paper was only published in 1939, and Gustavo was saying, well, those are the dimensional arguments that are used for the derivation of the law of the wall, and that's supposed to be the proof of the law of the wall. Plus, he introduced the concepts of the defect layer, of the outer layer, that were used by Coles in 1956 to propose the law of the wake. The law of the wake is called wake because the velocity profile resembles the profile in the wake behind a blunt body, behind a cylinder or something like that, or a profile close to a separation point. Now, the law of the wall became recently important, mainly in the 60s, because people started doing computational fluid dynamics, and again, approaching the wall was a very difficult thing to do, very difficult affair. So a chap called Brian Spalding, he introduced this very simple idea, you do the computations in the outer part of the flow, and close to the wall, you find an analytical solution, and you patch the analytical solution to the computations. So that saves a lot of time in computer time, and so the law of the wall became important for computational things, and basically, you don't specify the boundary, in many computations, you don't specify the boundary conditions right at the wall. You specify the boundary conditions at a certain distance of the wall, where the law of the wall is supposed to hold, and then you have again all those conditions for the velocity profile, the temperature profile, and you know K and the kappa, the turbulent kinetic energy, and so on and so forth. Now, the question I would like to introduce today and answer today is how prevalent, how invariant is the two-layer structure? So I have that, plot that Gustavo showed in the previous presentation. I introduced it today. Question is, suppose now I have turbulent flow. Does that structure remain? Suppose I have flow transpiration at the wall, fluid injection at the wall. Does the structure remain? Suppose now I have a rough surface. Suppose now I have heat addition. Suppose I have all these sort of different features. Does the previous structure remain? So what I'll do is explain that under many different conditions, the structure is still the same. It's very persistent structure. It's very robust structure. And just for the motivation, why we want to be able to solve the first principles and to give analytical solutions, again, to solve engineering problems. This is a very common problem. Anyone that boards airplane these days faces this problem. For low velocities, Mach number is low, and you have a supercritical flow, and therefore it works nicely. Trouble is, when Mach number approaches 0.77, many compressible waves, they merge together, and they form a shock wave, which strikes the airfoil right on top of you. Now, the large pressure gradient provoked by shock wave provokes separation, and that has a very detrimental effect. Lift goes bananas, and it's not possible to fly over Mach 0.77. So airplanes, they get bigger, they're more comfortable, but still, the time we take to go from Brazil to Europe is the time we took 40 years ago. It's a technological problem. Now, how do we solve that? One of the conceptions, one of the ideas in the 80s was to fit a plenum chamber right underneath the shock wave. So behind the shock wave, there would be suction. The suction would prevent flow separation, and the aircraft would be able to fly at higher speeds. Now, if you want to do that, we want to have some concept proof. I want to have some sort of mathematical proof that that's a feasible solution. I don't want to spend money and time doing, real scale models and so on and so forth to find out that that wasn't a very good idea. So we want to be able to find mathematical, analytical solutions to very complex problems as a proof of concepts. Trouble is, the interaction between shock waves occurs different ways, different configurations, depending on the strength of the shock wave and depending on the state of development of the boundary layer. So that's a perturbation problem with at least 4 small parameters, and that's really complicated to find an analytical solution for that. So again, we would like to develop tools, mathematical tools, so that we would be able to find solution to this particular problem. I'll come to that in a few minutes. But basically, what's my starting point for all the calculations? My starting point is always the Navier-Stokes equation. And what I'm going to do is, for turbulent flows, for the Reynolds average Navier-Stokes equation, I have 2 characteristic parameters. One depends on the global Reynolds number, and the second one depends on the fluctuations, the velocity fluctuations. Now, both small parameters are singular perturbation parameters, and that gives rise to what we call a nested boundary layer or something like that. So basically, if epsilon goes to 0, both terms, they disappear. I'm only left with the Euler equation, the inertia terms. And if epsilon hat goes to 0, the viscous terms goes to 0 as well. So, I have, for the Navier-Stokes equations, for turbulent boundary layers, I have 2 small parameters. I have to try to find mathematical solutions for that. There is a whole lot of mathematical theory behind that. I'm not going to go through that, but basically, what we can do is, we're talking about multiple scales. What we can do is, given the equations of motion, we can scale the equation in different parts of the domain, and we can find different local equations. These equations are different, and for the turbulent boundary layer, depending on the region of the domain, we have 2 equations which are sort of fuller than the other equations. I have one equation that embodies viscous and turbulent effects, and the second equation that embodies turbulent and inertia effects. If I solve these 2 equations, and if provided they have an overlap region, which is given by equation 10, the overlap region is exactly the log region, the log that is dominated by inertia turbulent effects. So if I can solve these 2 equations, if I can make sure that they overlap in a certain domain, I can combine the 2 equations and I can find a solution that's valid for the whole domain. So the whole principle of perturbation methods. You have an inner and outer solution, you match the 2 solutions, and then you find a solution for the whole domain. So that's the structure of the turbulent boundary layer for attached boundary layers. When you have flow separation, things they become much more complex. Basically, the viscous region becomes thicker, The log region becomes thinner, and at some point they meet together, and close to a separation point, the full averaged Navier-Stokes equation is recovered. So close to a separation point, again, the problem becomes much more complex, and all those theoretical parameters that I use to describe attached boundary layers, they do not hold anymore for separated boundary layers. So things become much more complex, and basically, we saw before in the previous slide, I showed here two different sort of red squares. This, in a separated flow region, these two red squares, they merge together, and we end up with only one sort of red square. So that's the motion equation, very close to a separation point. Now, before I have global equations and I have local equations, I can solve both. Solving a global equation, I have a global solution. Solving a local equation, I have a local solution. Now, this is a local solution. So I can solve this equation to find a local solution. Now, if I solve a global solution, I find an equation that spans over 10, 11, and 12. And again, global solutions can be matched together, and then I can find a solution for the whole domain. So basically, those are the solutions, local solutions for attached turbulent boundary layers and separated boundary layers. So for attached boundary layer, the solution goes as a log solution using the mixed length theory, and for a separated turbulent boundary layer, that's how the solution goes. And that's called Stratford profile. Sorry, that's called Goldstein's profile. That's very close to the wall and slightly away from the wall. We find this profile, which is called the Stratford velocity profile. So basically, at the separation point, the log function becomes a y⁻² function. Now, having found the local solutions, I can go back to my equations and I can find a global solution. The global solution under adequate limit conditions should reduce it to the local solutions. And if I find that particular global solution, and that's the solution that holds in that what people used to call the blending region, in the limiting cases close to the wall, it reduces to the linear profile, and far away from the wall, it reduces to the log profile. So that's the solution that, I mean, again, close to the wall goes to the linear profile, away from the wall goes to the log profile. And that comes from from a global solution. For a rough wall, C can be changed, and that's shown to be to hold for attached and detached flows. Now, having said that, now I have established I have established this two-layer model for the turbulent boundary layer, and I want to explore that under different conditions. Now, suppose now my turbulent boundary layer is compressible. Of course, the equation is much more complicated. I have to throw in the first law of thermodynamics, the equation of temperature, and so on and so forth. Things get much more complicated. But the way I have all my local and global solutions for the velocity profile, I have my local and global solutions for the temperature profile, and again, provided they have a common domain of validity, I can find a solution which is global for velocity and temperature profiles, and I can do that. The matching conditions are complicated. I won't go through that, but bear in mind, please, the two-deck structure for the incompressible turbulent boundary layer holds for the compressible turbulent boundary layer, basically. Now, combo number 2 is, suppose now I have my boundary layer and flow transpiration, flow injection, uniform flow injection at the wall, homogeneous flow injection. Now, the injection of flow at the wall defines a regular perturbation problem. So the structure remains the same. And basically, I can still find local solutions. I can solve the equations. I have now 3 small parameters. I can solve the equations. Now, in addition to the log term, I have a bi-logarithmic term. I have a log to the square term. But again, if I plot this on adequate conditions, if I plot that like that, I still can identify a log region for the flow. So that's, again, incompressible flow with transpiration at the wall. Suppose now I have turbulent, it's turbulent flow, compressible flow with transpiration at the wall. I can do the same, and I still have the same sort of velocity profiles. That's the comparison between experiments and theory, and I can succeed to find a solution for that, and equations for the friction velocity, and so on and so forth. Another combo number 4. Suppose now I have turbulence, transpiration, and heat transfer. Do I have a log layer for the temperature profile? Yes, I do. And I can solve the equations. Things get a bit messy here. I mean, the solution gets much more complicated. Of course, they have now to involve Prandtl number. But again, I can plot the temperature and the velocity profiles, and I can clearly identify a log region. So under that condition, turbulence, transpiration, and heat transfer, we still have a log layer. Now what I can do is turbulence, compressibility, transpiration, and heat transfer. We do all the computations. We have to solve all the local equations, and so on and so forth. And those are that's the solution, which again, it's very messy. I won't go to the details. But basically, if I plot the velocity profiles and the temperature profiles, I still can identify the log layer. And again, it's complicated. Combo number 5 is turbulence, compressibility, transpiration, and heat transfer. So it's complicated, but I still see my log regions. And I can make some, I can again find results for the friction, for the skin friction, and for the heat transfer at the wall. Now, regarding the motivation, that was the problem we were talking before. Now suppose I have a shock wave interacting with the boundary layer. Now again, things get much more complicated. I have to split the domain into different regions. I have to find local solutions for all regions, and I have to match them in the X and Y direction. So I have to match together 8 different solutions. It is possible to do that. Of course, things get much more complicated, but now I have a small parameter for the strength of the shock wave. I have a small parameter for the plenum chamber. I have two small parameters to to play the role of the turbulent boundary layer. But in the end, it is possible to find, for example, this equation. This is not a clean equation. It's very messy. Again, it's dirty equation. But this equation has to embody all the physics of the problem. The strength of the shock wave, the degree of development of the boundary layer, the suction and the injection velocities in the plenum chamber, and so on and so forth. But I still can, now I can find this sort of solution, and I can still provide that sort of predictions. So those dots are the experiments, and the ones on top of it are the simulations. Of course, for very high Mach numbers, things are much more difficult to predict. But for Mach number of the order of 1.3, I still have a very good algorithm between solution and combo number 7. Now I can mix turbulence, roughness, heat transfer, and unsteadiness of the thermal turbulent boundary. I still can find a local solution. It does not involve log terms anymore. There is a term now which is zeta, log zeta, or y log y, where zeta is the distance from the wall, but I still can identify a log region, and I can plot those sort of profiles. Of course, when you have roughness, the profiles are dislocated close to the wall, because you have what's called the error in origin or the displacement in height. But it is possible to identify here a log region. And then I come to this case, which is really complicated. That's flow separation. Flow separation is much more complicated. I'll flash for this. Basically, when you are far away from the separation, you have a very well-defined log region. And as you're approaching separation, the log region starts to decrease, and eventually it becomes a 1.5 region. And it is possible to find one single mathematical solution that reduces to different cases according to the distance you are from the separation point. You recover the log behavior when you are away from the separation point, and you get the Stratford behavior when you are close to when you are at the separation point. Again, using all those expressions, this is the flow behind a hill. Those are the computations using the previous expression that was deduced derived for the problem. And this is the experiment, and this is the computation. So it is possible to reproduce the flow, the recirculating flow region using that sort of solution for the near wall region. That's a different combo. That's again turbulence, separation, and roughness. Again, it is possible to do the same. We can sort of find a local near wall solution that upon numerical simulations gives good results. And I'll flash that as well. And again, the other thing which is possible to do is to consider turbulence, separation, and heat transfer. And that's a very good thing to do. Now, there was this question before about non-Newtonian fluids. If you have a non-Newtonian fluid, a pure viscous fluid, the two-layer structure remains for the turbulent boundary layer. That's very interesting. The thickness of the viscous layer changes, but of course, and that was complicated because these experiments are really difficult to do. And with one of the postdocs in our lab, we did some direct numerical simulation, and basically we found those are the experiments which are difficult to reproduce, but through direct numerical simulation, we found this graph with this particular definition of the log region. Trouble is, the level of the log region now depends on the index of the, of the power law for the boundary layer. So the level of the wall depends now on B divided by N. On B is 5. A is still a constant. But again, everything can be applied. It is possible to define a skin friction equation for all that. So for a purely viscous fluid, the two-deck structure of the turbulent boundary layer remains the same. It is conservative. Someone showed before, I think it was Pinak, he showed a mood graph for Newtonian fluid with Nicolaides and so on and so forth. So that's the mood graph for a power law fluid. You can do that from direct numerical simulation, and that can be reproduced in here. Finally, I think that's the last combo, and that's turbulence, transpiration, roughness, and in-pipe flow. So what's the application here? Petroleum engineering. You have a pipe that goes, you drill your horizontal pipe, you start producing oil. Of course, the surface of the pipe is porous. It's a distributed injection, and we want, for the purpose of design, we want to evaluate the skin friction. How do we do that? Again, we find a local solution. We integrated that local solution of the cross-section of the pipe. We find this skin friction equation, and we wanted to compare that equation with some experimental data. The gentlemen that did the experiments are sitting at the back of this room. It's a very complex experiment. Basically, we have this horizontal pipe. This is representing the rock. We inject the fluid in a plenum chamber, and through transpiration, the horizontal pipe starts producing fluid, oil, whatever. And this is really new data. I just received this data a week ago. And that's unbelievable. I really have to check that because this is really unbelievable. I don't believe that myself. And we really have to check that because those are the theory is in here, the empty symbols. And the green symbols, they are not very visible, but they are the experiments. They are really close together for no transpiration or for different transpiration rates. And that solution comes from the first principles. You get the Navier-Stokes equation, you average Navier-Stokes equation, you find the local equations, you solve that equation, you integrate of the whole domain, and then you find the results. That's not experimental at all. The solution that comes from first principles, that comes directly from the Navier-Stokes equation. And they are very useful. To conclude the talk, what I wanted to show today is you have this classical structure that was introduced before by Gustavo. And under different conditions, the structure remains. It becomes more and more complex. But again, you can find your local solutions. You can find your skin friction equation. You can find your mean velocity profiles, and so on and so forth, under different conditions. And again, I didn't explore all the different conditions here. But for impinging jets, or riblets, or changes in surface, all that was said today, it could be applied. Finally, just to conclude, if I have some time, do I have internet access here? Do we have internet access here? I wanted to run this simulator over the internet. Not quite sure we are going to be able to do that. How do I access internet over here? Luther. Right. How do I do that? Sorry, I wasn't using. Yeah. No, it's with the mouse. Okay. Yes, I want to. Yes. What? Okay, the export is there. Okay. Anyway. Yes. Yeah. That's gonna be. Yeah. That's gonna be fine. Internet. No, internet. Thanks. Sorry for my clumsiness, but anyway. I hope I'm going to get in there. If the internet is really working, it's very slow. I hope it's coming. Or else I'll give up on that. But basically, what I want to show is this real-time simulator for pipe flows with wall transpiration, and because we are actually well, okay, I'll rest my case. Never mind. Thank you very much. Abriu. Well, just because I have finished the rest of my case, if I can do that, it's going to take ages. But anyway, please, I'll handle to the chairwoman.
Okay, let's, thank you, Dr. Freire, and let's move on to the questions. Maybe the website will load during the question sections. Are there any questions or comments or?
Well, I have at least two questions, but
no, it's okay, no problem.
So the first one would be, I'm sure you're very aware of the work that Chorin and Barenblatt did using intermediate asymptotics.
Yeah.
They argued
and other people as well,
in favor
of a power law. Of a power
law
yeah.
Instead of the law of the log. Yeah. And what I'm curious about is whether any of these particular combos that you considered could be either used to rule out such a power law or to say that maybe such a power law gives you a better understanding
the power law
fit
the power law and
then you'd get out of the law of the law.
Yeah. The power law and the log law are cousins. You know, you are mathematicians, they're almost about the same thing. Trouble with the log law is that the log law has, let me think here, 84 years of good service. And there is a lot of material that was developed using the log law. Now, if you're working in the aeronautical business and you wanted to do some skin friction predictions, you'd come to me and you'd say, well, if it is incompressible flow, it has to be right by 3%. If it is compressible flow, it has to be right by 5%. The log law does give you that 3 and that 5%. And again, it has given you 84 years of very good service. Now, how on earth do you want to retire the log law and you want to adopt the power law? So that's one of the things. The other thing is,
that's not really germane. I'm not advocating
the
intermediate asymptotics.
But I think, again, people started with that wave in the early 90s. It stayed with us for 10 years, and then, it sort of dissipated. So no one talks about that anymore. I don't think anyone talks about that anymore. Sorry, Alex. Second?
Again, that's not what I'm asking.
Yeah.
But okay, I'll go to my second question. And thinking about the power law fluids that you studied, it seems to me that there's an opportunity to understand something, and actually I found it intriguing that you get a shift. So B becomes B divided by N.
N, yes.
And this is, so you can treat, of course, both the shear thinning and the shear thickening
Yes,
alternatives
yes, yeah.
simultaneously.
Yeah.
And so it seems to me that this offers an opportunity to understand something more about the distinction between power law and conventional Newtonian
Yes,
influence,
yeah.
and moreover,
Yeah.
the distinction between shear thinning and shear thickening
Yeah.
power law fluids.
Yeah. Yeah, again, we did the DNS results. Of course, even for these purely viscous fluids, there is a layer which is really dominated by inertia, and then the spectrum, all those arguments, they remain the same. But there is lots to be understood. Yes, that's it. Right.
Any more questions? No, so let's thank the speaker again.